This is the next video, and I'm going to talk about the difference between geometric mean and arithmetic mean, and what's the difference and when to use what, and so on. As you know from the normal high school stuff that even in your previous studies, you definitely, and everyone knows that the mean that we always refer to, it's actually the arithmetic mean when we say mean, or average. We never said arithmetic or geometric. We used to use the arithmetic without even saying that this is an arithmetic mean. The arithmetic mean is the usual one by making summation of all your elements and divided by the number of data points. This is very good and very representative, but when it comes to percentage, and especially when it comes to financial sector, they don't really use the arithmetic mean to calculate the average or the mean of the interest rate throughout or over a couple of years. They always use what they call geometric mean. You need to know the difference in terms of calculation. So if you look at here, suppose you put 1,000 into an investment that grows 10 years in the first year, 20 years in the second year, and 60% in the third year. The average rate of growth of your investment is not 10 plus 20 plus 60 divided by 3. It's not anyway in anywhere or near to be 30 because it's wrong. But in this case, we calculate it in geometric mean. Geometric mean, based on the discussion here, it's basically all what you need to do is not to add them, is basically multiplying them and take the nth roots. So if you have 3 years, then you're gonna take the what we call cubic or cube, not the square root, the cube root, and so on and so forth. So if you have 5 years, then you're gonna take the fifth roots of the multiplication. So in this case, you can look at here down here. It's 1.1 because it's 1 plus r. R is the interest rate. For the first year, it's 1.1. The second year, 1.2 because it's 20%. The third year, it's 1.6 because it's 6%. If you multiply all these components together and take the third roots here, then you're gonna get the R equal 28.3%, and you can see there is a difference, and it could be very big difference when it comes to high investment. 28.3, it's really different from 30. So you might really say the difference is not really significant. No, it is. When you have low amount of investment, yes, maybe the difference is not that significant, but we are talking here about high number of investment. Definitely there is a difference. So be careful when you being asked to calculate the mean or the average. You have to understand in which situations. Okay. Now, one of the very important parts when it comes to data analysis is to show how the data are spread out around the average, and sometimes there are multiple ways to represent or present the data. One of them is to present it in a graphical representation, and sometimes in a quartile. Let me give you an idea about what I'm trying to say here. Again, I'm going to take a pen here just to draw the data. Imagine that we have data that looks like this data. Imagine that we have an array of data, like a column in Excel sheet, one column, right? So, and this data is shuffled. Imagine that we sort the data first, and then when we sort the data, if we have 100 item, we're gonna sort it, so it will also be 100. But just for representation, imagine that you sorted the data in descending way, like here, just for the sake of making it visually understandable. So that means this is the maximum value here on the top, and the minimum will be here on the bottom here. Okay, so this is after you collect the data and you sort the data. if you go to the middle of the data, all of you guys know that the middle of the data is the 50% of the data are less than, will be, it means the 50% of data are less than this value. So this value, we call it Q2, 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 because it's a second quartile or the median, or like actually let us call it median. In fact, it's median because you know it from previous videos or lectures, the median. But if you also, let me grab another color here. Okay, let me take this. So if you also get the half of the first half and the half of the second half, you're gonna get here 25% of the data, and definitely you're gonna get here similarly 75% of the data. So if you think about it visually, sorry, here, okay, you understand what I mean. Okay, so visually, let me see if control, oops. Oh, I did something, I don't know. Let me see where I am now. Oh, I did something wrong here. Okay, so maybe I was flipping up and down here, but this something happened on my computer, but it's okay. So here we call it quartile 1 because this is the end of the first quartile. We call it Q1, and here definitely at 75 percentile we call it quartile 3. For that reason, you can see here there is an area in the middle. Let me see if I get yeah, something like that. Let us take yellow one. So this area now you can see represented by the difference between Q3 and Q1, and you can see here Q3, Q1, we call them interquartile range. And can you imagine that this interquartile range includes 50% of the data? Because why it's a 50% of the data? Because obviously this part is 25% of the data, and this is another 25% of the data, of course. So this is the 50%, 50 percentile, or 50% of the data. So interquartile range, if this yellow box here, it looks like box, right? So if this box is wider, still 50% of the data are inside, but if it's wider or narrower, irrespective of the size, it still has the 50% of the data. But if it's wider or smaller, it indicates how the data are spread inside your data set. For that reason, we come to what we call it Boxplot. You can see the Boxplot is here. It's kind of trying to represent it in a way to make it easy for you to see how this Boxplot is being constructed. So by having Boxplot, we can calculate multiple components here, or numbers. One of them, the first quartile, as I showed you before, the second, the third, and the interquartile range. And not only that, we can also calculate what we call it whiskers. Here it's the first whisker, it's a Q1 here, and this one minus 1.5 multiplied by IQR. Then you get this value here. So this is basically somewhere, it's not the minimum, but there is another value here. This is 1 here. And we can also calculate the upper one, which is positive here. You take the positive part, but obviously it's greater than Q3, so you might really stop somewhere here. So basically it's not the maximum or minimum. This is the upper whisker, this one. And let me correct something here. Let us say this is a second. Let me take another, let me take the green one here. This is actually, it could be here, not the minimum. So I'm gonna remove this, but this is actually could be here. So this is very important. This is the lower whisker, and this is here the upper whisker. Why we need them? Because they are helping us. If we have any data point here greater than, between the maximum and greater than the upper whisker, we call it outliers, or even here. So let me take another color here to make it, yeah, let me take orange hopefully, or a little bit yellowish. So if the point are here, anything here will be outlier in this area, or in this, sorry. Okay, let me erase it in this case. If there is eraser here, okay, let me erase this one. Okay, back to here. I'm gonna take also this pen. So this area also will include all outliers. So this yellowish area, any point in this yellow area or range, whether on the upper level or a lower level, we call them outliers. Okay, outliers are extreme values. We need to deal with them in a later stage. So let me go down here, see what we have again here. So the spread can be seen, as we mentioned, about quartile and boxplot. So you have seen boxplot now. We're going to show you one of the videos today, or during this discussion. It's up to you whether you want to see it today or tomorrow, but in fact, or to show you different ways to represent your data. So now we're still on the spread discussion here, and we need to look at the spread from the idea of population variance here. So population variance is one of the very important concepts, which means how each data point varies from the average here. So basically, the very important concept here, what I want to really to share with you, let me show you what I mean here. So I'm going to take this now. So imagine that the data are spread in a way like this one, and you find an average here. So the average is here. We call it y bar here because it's average. So if you try to find out each value, how far each value far from the average, you might really find some of them, they are lower. So here, this is the lower here, so it will be negative, or maybe higher, so it will be positive. So each point here on this line represent a data point, and if you want to see the difference between this point and the average, and this point and the average, and this point and the average, and also you might really have here another one here and here and here, so you can see the difference between this value and y bar, this value and y bar, and so on. So all these differences will be negative, all these differences will be positive, but if you take the summation of positive and negative, you're going to get really zero when you want to make a summation, because the summation is, the idea is to summarize your data. Instead of looking at the difference of each data point, you want to see that summary of all differences, and you might really take the summation, and definitely the positive will cancel some of the negatives. You end up by having a zero. For that reason, we use this square to get rid of the negative. So every point here will be up here, here in this case, and this will be also a square. So if we square them all and we take the summation, the summation symbol here, sigma, and divide by n minus 1. This is n minus 1. It's a little bit complicated topic. Just skip it for now. We can explain it later on. But this is what we call it degree of freedom. Degree of freedom is very important concept in data science. But for now and for your the level of this course, we don't need to pay attention to it for now. But we're going to talk about it later on at the later stage of this semester. So n minus 1, we get the sample, what we call the sample variance. But if you have population, remember the mu is the average or the mean or arithmetic mean of the population. We call it mu. And if we have the population, we divide by n. So be careful when you are asked a question. You need to ask this: are we calculating the variance for the sample, or we are calculating the variance for the population? It's very, very important, because if you are calculating for variance, you're going to divide by n minus 1 for the sample. But if you calculate the variance for the population, you're going to divide by n. So I hope this is clear. And the smaller the value is, variance, in this case, it means most of the points are really close to each other. So if I may draw a histogram for two situations, if the standard deviation here, or the variance, I mean, it's smaller, let us say here, of standard, here the variance of A, we have A case here, and we have another case is called B. So if the histogram look like this, or histogram, and here the histogram looks like that, so you can immediately know that the variance of A is less than the variance of B. So it's less than, so this is less than. So less than, it means most of the points are close to each other. If it's the variance is large value, it means most of the points are far from the average. So we hopefully know that the average is the middle. Not most of the time, but it depends if the data is symmetric. If you remember from the previous videos, the difference between skewed data and symmetric data. So if you take the square root of each of these value, you're gonna get to what is important for us here. It's called standard deviation. So standard deviation, it's basically, it's the one of the very interesting component. It's basically, it's one of the things that we like very much to use it instead of using the variance. Why? That if we have our data here, let us say that our data will be in dollars. Imagine that. So if we have average like y bar here, the average of our data will be also in dollars. If you calculate the variance, you can obviously see the variance is a square, so it will be dollar square, right? So physically we don't have data dollar square, because usually I don't have dollar square in my bank. I have only dollars. So basically we don't use dollar square. For that reason, we take the square root, we get the S. So S, standard deviation, is really dollar back to dollar. For that reason, we always prefer to use standard deviation instead of variance in order to represent the spread of data, because we understand that they are $5-6 away from the average. But if you say it's a $25 square, doesn't really physically rings a bell with anyone. But again, in order to calculate the standard deviation, you can see you need to calculate the average first and the variance second. So first you need to calculate the average as first step, second step to calculate the variance, and the third step to calculate the S, to take the square root. So this is how you have to pay attention to this thing. Last part for this video is basically two concepts here. One is instead of using only the average to compare two groups, if you imagine that you have group A in grades and group B, so you might say if group A, their average is let us say in terms of percentage, they got really 75 as an average, so it's obviously less than the group who got 80 as an average. So you might really say B is better, but if you look at the S as another value to see how each one is varying, imagine this is say it's a 10 grade here, 10 standard deviation of points, and here they are also not 10, in this case they are 8, right? This is less. So you might really say this is 10, it means most of the students are varying around the average higher than here. So it looks like here it's better in terms of most of the students are close to each other. But this is not the case. The case you need to divide the S by Y and divide and multiply by 100. So if I take this is the S and this is the Y bar, the average. So basically if you take the CV here, we call it the coefficient of variation, by taking the S divided by Y, let us see the number that we're gonna get here, 100, sorry, 1000, oh sorry, 110 divided by 75. And here it's basic, and multiply by 100, right? So it's be careful here. And here's the same thing, 8 divided by 10, or 80 here, and multiply by 100. So basically you're gonna get here, it's a 10%, which is variation is basically looks like that. But when you come here, is basically you are more or less you can 3, 4, 25, 7, 7.5, something like that, 7.5 percent. Yeah, if you want, we can easily calculate it here just for us here to, this is A, this is B. So all what you need to do is to take here, this is the easiest one here. You take the 8 multiply by 80 and multiply by 100. So divide, I mean. But here it's equals, I take the 10 divided by 75 and multiply by 100. So here's 13% in fact, which means the variation is still higher in this group than this group. So you can see CV, it's a very good way to make a comparison between data, but it's like combo. It's not only average against average, not standard deviation against standard deviation, but it's actually both together in one component, and this is what we call coefficient of variation. It's being used a lot, to be honest, in stock market. If you have stock A and stock B and even stock C, the higher the CV, it means higher risk and high volatility. So it's a very important application in finance. Last part, or the previous, last part here, it's related to Boxplot. Let me see. I might really, I think it's better to put it in another video. So I'm going to stop this one again, and the next video, it's going to be about the Boxplot again. Very quick to have an example, and then to see how the Boxplot is being used as a comparative tools among different situations. And then we go through another topics called standardizing data, very important. And then we're going to go to the time series plot and the transformation of data in case the data is extremely skewed, and how can we deal with this kind of data. And this will be the last video in the next one. But after this video, I'm going to take you through Excel to calculate a couple of things that might be very interesting to you. So see you in the next video.